So as Alex mentioned, this is going to be an introduction to async in Rust. I'll try and talk about async in the broader sense, then specifically in Rust, what that means, go through a few runtimes, in Tokio, about async-std, tiny bit about futures and small, briefly mention async traits, and then as an aside, mention scope threads at the end. And then the idea will be then after the talk, people can kind of have a bit of a free-for-all discussion and hopefully get other people's thoughts. This is very much just a primer. So what is async programming? Well, it's a concurrent programming model where the syntax allows sequential looking code, but instead of returning the type that your function looks like it's returning, you're actually returning a task or a future, which will then continue the work instead of completing it before continuing. So when people talk about async, they often in the same breath talk about parallelism and running your code in parallel. For tasks which have to wait on something, that's normally where you use async rather than just where you want to do lots of work and make use of all your threads. So an example would be listening to a port with a TCP listener. Could also be to do with file interaction. For compute heavy tasks where you want to parallelize things with no waiting, you don't really want to use async in Rust necessarily. You're probably more likely to want something which is specifically a data parallelism library like Rayon. Found this quote on the internet, which I think is quite nice. Threads are for working in parallel and async is for waiting in parallel. And that's a good motto to have in your head if you're wondering, do I need to be doing this all asynchronously, or do I just need to be doing things on multiple threads using something like Rayon? So an example that you'll kind of hear coached about is cooking breakfast for something where you might want to do things asynchronously, because the tasks like frying your eggs and cooking your hash browns and toasting bread take time where you're not actively having to do anything. So yes, you could do things in parallel where you could have multiple people cooking eggs and cooking hash browns, but really one person can do this by putting on the eggs and then waiting until they're done. And while they're waiting for it to be done, cooking the hash browns. And while they're cooking the hash browns, once they put them on, they can then toast the bread, but they don't need to sit there and watch it. But there are some tasks that will be dependent on the results of that. So you can't butter your toast until you've toasted the bread. You can't add milk to your tea until you've brewed the tea. So that's the kind of model that we're working with. You've got things where you're waiting for something to happen before you can go back and carry on doing work. In the context of Rust, Rust provides very kind of minimal architecture out of the box. But those primitives allow the ecosystem to then provide its own third-party executors. Those core primitives that it provides are the future trait in the standard library, an async keyword, and await syntax. I'm going to go through those now. So the future trait is something which you don't usually have to interact with directly too much, but it very much underpins the whole model. It's this idea that you have some object, you don't know what it is, you just have some type somewhere that implements this trait, and it says, I'm going to return the type that you want your function to return at some point. I can return it in the future, but I'm not necessarily going to return it straight away. It has this ability to be polled, and when you're polling it, it will either tell you the future's not ready, there's still work to be done, we don't have the value yet, or it will say it's ready, and that means it has the value, you can get that value out and you can continue the work in that particular function. The next thing I mentioned that it provides is the async keyword. So when you mark a function async, what you're saying there is, I'm not actually going to return an unsigned 32-bit integer right now, but I will return it at some point. What I'm going to return now is a future, and that future will have the output type of unsigned 32-bit integer. And that's the kind of syntactic sugar that it's providing to make it much easier to read and write your code. And that works hand in hand then with await. I'll just show you that those do indeed return the same type. So this is just a screenshot from VS Code. You can see using the async syntax, I'm still getting that returning of a future, and using explicit return, it's exactly the same. The await syntax is where things get a bit more complicated and require a bit more thinking. What await does is it yields back to the executor, to some executor, and the executor will be the thing that actually makes the progress, does things like polling the future. And that executor is provided by a third-party library, and that within that executor context, it might run the task to completion, it might do a bit of the task, go and do a bit of another task, and then come back to it. You don't know, it's kind of a bit of a black box for you. But the syntax allows you to describe the kind of cooperative scheduling of tasks. So you can still say, you know, I can't do this task until this is complete because that's why I'm awaiting on it here. But there's other things that might be happening at the same time that it can then cooperatively intersperse when you're, for example, waiting on a TCP port or waiting on a file. The kind of features of async in Rust are that futures are inert. So they're not quietly doing things in the background. They're only going to make progress when they're polled. And dropping a future will stop it from making any progress. Async is kind of zero cost, which means inherently, you know, the bit that Rust provides isn't doing anything special. So you can, in theory, use it without heap allocations. You can use it without dynamic dispatch. There still might be cases where you are using it with heap allocations and dynamic dispatch, but it's not out of the box going to do that. You know, it should be zero cost when you need it to be zero cost. As I mentioned, there's no built-in runtime. So there's no, that executor is provided by the runtime. The runtimes are provided through community maintained crates like Tokio and async-std, and those are things we're going to cover next. As a result of those runtimes being available, and just by the way they're designed, some of them are single-threaded, some of them are multi-threaded, some of them can be set to single-threaded or multi-threaded, but each of them have their own kind of different strengths and weaknesses. So we've said that it returns a future. Just to kind of reiterate, when does that task actually run? Well, the executor at the top level somewhere will be polling futures until progress can be made. A really basic, kind of not smart executor might be polling those futures in a loop until they complete, just kind of holding onto them and saying, is it ready yet? Can I do something? Can I try and make progress? But that's not how they'll work in practice because it won't be very efficient. There are better ways to do it that we'll kind of come on to. Starting with Tokio, which is by far the most common runtime that's used, and it provides, as mentioned, that kind of top level loop, which is the thing that handles the futures that it's holding on to. And it also, hand in hand with that, provides low level resources like network sockets and timers. And it's really important that it provides both of those things because they kind of speak to each other. The executor in Tokio is what holds on to the state about what resources it's waiting on. So as I mentioned, you might be waiting on a port. It would say, okay, this is where I'm going to hold the information about that port. The reactor is what interacts with the operating system. So this is the way that your executor can be a bit smart. So rather than just iterating through this list of futures forever, instead it can go to sleep and defer some of that work to the operating system and say, look, the operating system is in charge of this. You know, it knows when there's activity on this port. It knows when there's something that I can read from it. So I can get the operating system to just wake me up if any of these file descriptors change state. So it will be interacting with, on Linux, it will be epoll, on Windows, it'll be IO completion ports, and on Mac, it'll be something like KQ. And it does that via a crate called Myo, which I've never had to use, but this is what it's good for. It can handle those interactions with the operating system. The runtime also handles waiting on non-operating system events. So you might be waiting to receive on a channel. So if you remember the fearless concurrency chapter where we sent information over multiple producer, single consumer channels, that's one of the things that it can wait on, and Tokio provides its own version of that as well. So there's a few kind of key bits of Tokio that I wanted to draw out as things you kind of see a lot and are useful to talk about. Those are Tokio main, which is the way you annotate the main function to make it async, which we'll kind of come on to. Block on, which is the bit that actually runs a future to completion. So if you called block on, you're saying, okay, actually just do all of this now. No more kind of yielding back to anything else. There is nothing more for you to yield back to. So this is where it would become synchronous. Everything above this would be synchronous. Await, which as we mentioned is how you yield back to the executor who's trying to make progress on the task. and await says, don't do the code after this until this is done. You can be sure that you've got the result after that. Tokio spawn for creating asynchronous tasks to be executed, which are communicating this can run in parallel. It doesn't necessarily mean it will run in parallel. Spawn blocking, which is for CPU blocking tasks, things that require a lot of CPU. They're not waiting on things necessarily. And then joining tasks, so saying, I don't mind which of these completes first, I just want them all to be done. So this annotation that you put around main allows you to write async function main. But this is not an async function. Main is not an async function, but it's a really convenient syntax to make it look like your function is main. Your function main is async, and allows you to just immediately call await on things inside it as if it was async. But what it's actually doing is it's expanding to something like this, and this is where we'll start seeing block on. So our main itself is actually here just still returning a result. The body of our main function that we wrote here, which was calling some async function, would go inside our async body here. And then the main itself is just, so we're returning a Tokio runtime builder, which crucially this bit at the end, blocking on this async body of the function. So we've immediately got this call to block on. And that's kind of the first place you'll see it. And it's where your asynchronous code becomes synchronous. And that's your top level. Everywhere else should be kind of ideally async all the way down. The await keyword is that thing we mentioned that yields back to that top level executor, which is inside this Tokio runtime. So in this case, we've got a TCP listener, we're binding to a particular port, and then we're awaiting on it because we can't do anything until that's completed. This is at the kind of the top level, so there isn't actually anything else that would need to be interspersed with it, but later on in our code, there could be. Here we're then accepting things on that listener and awaiting on that. So we are looping until, and we're trying to get information, but it's not necessarily immediately going to have something at that port unless something sent something to that port. So it will just be waiting for the operating system to say there's something here. And that's why you would want the await keyword. But what's important to note about this code is it's only going to process one socket at a time. So it can only do one thing at a time, because that await keyword means it's blocked. It's not blocking the thread, but it is blocking this particular execution path. So it's yielded back, but it's not going to carry on and go on to the next line of the loop. If we wanted to do that, we would want to use something like Tokio spawn. So this is what you use for tasks which can be run in parallel. And it's going to schedule that task on an asynchronous green thread, which means it's not a true operating system thread. And it's not necessarily going to run in parallel, but the executor is allowed to run it in parallel if it has access to more than one thread and it decides to. That spawn is going to return a join handle, and if we need to get the result out, then we can await on that join handle to get the result out. And as a result, the usual multi-threading rules apply. So you can't share data without wrapping it in something like an atomically reference counted mutex lock type. We're going to go back to the Phyllis concurrency chapter, or you could send data using channels. So the way that would look, modifying the code from earlier. So again, we're binding the listener to the address. In our loop, we're then moving our processing onto a separate thread. So this accept will be when it receives something at this port, but we're no longer having to wait for the processing. So as a result, it can then go back to the next loop and listen for something else coming into that port, and it can do all those processes independently. There's kind of an implicit assumption in async code that you're going to be awaiting frequently, and that there's going to be things that you're waiting for, that there is going to be time where other tasks can be interleaved with the current task. If you've got just a really compute heavy operation, then there's not going to be a yield in there necessarily. There's not going to be an await somewhere partway through. So any other tasks that are scheduled aren't going to be able to run while that one is running, because it's never going to yield back to the executor. The executor can't schedule anything else afterwards. So as a way of making sure that doesn't happen, you can indicate to Tokio, you can say, look, actually, I don't want to run this on the current thread, but I don't want to, I don't want it to run concurrently with the other tasks. And the reason I don't want it to run concurrently is because I know that it's not going to kind of interoperate with them. It's just going to basically block, even though it's not technically a blocking operation. So you have this spawn blocking in order to say this is some compute heavy work or synchronous code. And those spawn blocking threads, like green threads again, are not going to be doing that kind of heavy interspersal of tasks. So you're not going to end up, this isn't going to block up those other async tasks that are weight driven, not CPU bound. And the final thing on this one is joining. So if we have multiple concurrent tasks and we can't continue until they're all done, rather than awaiting on them one at a time where we don't even start the next one, because remember that won't actually execute, none of that code will execute until the previous line is done. So instead of doing task 1, await, task 2, await, you can instead do join, which is a macro that can take a variable number of asynchronous tasks, and then it will wait until they're all done, but it won't, it will be executing them all concurrently. If those asynchronous tasks returned results, then we could also use try join, and that's a way of preventing doing extra work if you're not going to continue anyway. So if one fails, you just can drop the rest. Async-std is another very common runtime. It's modeled against the Rust standard library, with the idea being that you can replace components that you are used to out of the standard library, but they'll have an async counterpart. Similar to Tokio, it provides an executor, and it provides low-level resources like file system operations, network operations, timers, all those things that we just talked about with Tokio. And again, this slide's going to look very familiar. We have an async-std main, which is the equivalent of our Tokio main, with very similar functionality. We've got block on. We've still got that, the await syntax we've said is part of the language, but it's going to behave in the same way. We've got async-std task spawn, and we've got spawn blocking, and we've got join. So we've got all those same moving parts that we wanted. So here's the main function here. We're calling into some async function that does some async things. If we use cargo expand, we can see what that code actually looks like. Here they've got a slightly funny looking thing where it's function main, async function main, but the essence is the same. You've got your asynchronous function is wrapped inside an outer synchronous function, and we're using block on to signal, okay, right, now it's time to actually do some stuff. The executor is going to go through these futures in a sensible manner. It's going to interact with the operating system to wait for things without blocking, and it's going to execute all of our work. Got this async-std task spawn, which again is for tasks that run in parallel. It's running on an asynchronous green thread, and the executor is the thing that actually decides whether they're going to run in parallel. So this syntax is, I've switched it for async-std, but honestly, you couldn't really tell the difference because it's a different include for the TCP listener. Because as I mentioned, it's the TCP listener provided by that particular runtime, the async-std. It's not the Tokio one anymore. But the rest of it, it's almost identical. And the reason why it's important for those types to match up, where you have to use the async-std TCP listener, you couldn't use the Tokio TCP listener or the standard library one, is that it's keeping a handle on all of those things at the executor level. It's making a note of what are the things we're waiting on, so that it can do intelligent wake up. It's not just naively polling futures until they're done. Spawn blocking, again, the syntax is almost identical. It runs the provided closure on a thread dedicated to blocking operations. And that way you're not getting in the way of all of your IO bound operations with something that's CPU bound. We have a join macro. What's slightly different here is this isn't provided by async-std directly. This is provided by the futures crate. So the futures crate has the join macro in, and it works with async-std because async-std is based on the futures library originally, and they can interoperate very well. And there's also a try join with the exact same behavior as Tokio. I mentioned the futures crate just then in the context of async-std using it. What's cool about the futures crate is it predates the async await syntax. It worked in isolation, providing a lot of these things, but without the language support that really brings the async programming kind of into its own and makes it much easier to use. But it still provides really useful things. So it provides its own version of the future trait, but there's also a future extended trait that provides additional useful, convenient adapters. It provides its own multiple producer, single consumer channel for passing data. It also provides its own executor, just like Tokio does, just like async-std does. It provides its own block on, and it provides a bunch of other useful helpers as well. So the equivalent main of what we've kind of seen earlier is slightly different. There's not that annotation, or I couldn't see any in the doc for, there's no procedural macro to transform our main for us from an async main, so we're explicitly calling block on, but in essence, it's the same kind of code. There's other runtimes, so I've just given one example, which is small, which is again kind of based vaguely on the futures crate, but I think it's very lightweight, and it doesn't necessarily rely on the standard library even being available for those kind of certain embedded cases. But the syntax is, again, very similar. You have block on, which then inside will have your async method that will have awaits all the way down. It doesn't provide all of the things that async-std and Tokio provide, but it's a good kind of minimal set. So you've probably started to notice there's some kind of common abstractions across all of these runtimes. There's this idea of spawning a new task, starting a timer, plugging tasks into each other and kind of combining them. There's also things like async read and write traits, which some things provide and not others. And ideally, you would want it to be such that you wouldn't need to know what runtime is underneath an operation, but that's not the kind of current situation we have. You can't mix and match Tokio and async-std easily yet. So Tokio's types can't be used outside of a Tokio context for a start. So if you try and use any of those Tokio types when you've got an async-std runtime, then it's going to panic. And Tokio and futures have very similar things in them, but they are different. So they each have an async read, they each have an async write, but those aren't the same. So there's a crate async compat that provides adapters between these types, which gets you some of the way, but I think there are kind of, from what I've read, vague plans in the future to try and make these things a bit more friendly to use together. As I mentioned, there's this async compat trait. So if you needed to go from a futures executor here, but you needed to use Tokio functions inside, then you might have something like this, where you've basically wrapped it in this compatibility block. So you are actually able to use a Tokio runtime in that little pocket of code. A couple of other things to mention. You can configure these runtimes. They're not just static. Well, no, they are static, but they're not something that you don't have control over. So with async-std, there are environment variables you can set for things like the thread count and the thread name. And similar for Tokio, in the builder at startup, rather than using the Tokio main at the top, you could explicitly create your runtime, and you can set in the number of blocking threads. You can also set in the number of core threads and a name prefix, stack size, bunch of different things you can set in there. It will default the number of threads to the number of cores on your machine if you don't set this, which is a pretty sensible number, but just in case, you know, for some reason you shouldn't use that. Or there's also the case where you might want to have multiple runtimes in theory. So if you wanted that, then you might have one just using 2 of your threads, and you might have another one using the remaining 2 threads or the remaining 4 threads, or however many you have. Another little aside, we don't yet have kind of out of the box async trait functions. So you can't write a trait called read async, which has a read method in it, which is asynchronous. That's not a thing that exists. The reason for that is that the state that you're in when you yield at an await point is stored in the future itself. So this async function, but remember the desugaring of that async is to return an impl future with an output of the same type that your async function was returning. But the actual concrete type itself will be variable size depending on how much data you need to store in it. It ends up being kind of a union of all the possible yield points in your function. So it doesn't know the size, and as a result, this isn't going to work. If you desperately need this, then there is a trait called async trait, where you annotate your trait and you annotate your implementation of the trait with async trait. And it transforms the function so that it returns a pinned box dynamic future, also the send trait and async trait lifetime. But that's a heap allocation and it's dynamic dispatch, so it's kind of not ideal. And I think there are people working on this and trying to fix it, but I'd be really interested at the end to hear anyone's thoughts about stuff like this if you know anything about it, because I'd also be curious. Just to show you what that would look like, you've written trait file async function read. If you do cargo expand on this, you can see it ends up with this big old mess, but it's essentially the same as what was showed earlier. So it's pin, which is to do with the memory, box, and then dynamic future send async trait. Cool. The final thing I wanted to talk about is scope threads, just briefly. So this is because this is kind of new and shiny and vaguely related. Without scope threads, if you know that a data is going to be alive for the duration of your thread, you still can't use it. So here I've got my string slice, and I'm saying, okay, I want to print it, but I'm going to do that on a separate thread. I'm going to spawn the thread. Now I know that that thread is joined on before the string goes out of scope, but the borrow checker doesn't know that. So we're going to get an error. It's going to need to either have a static lifetime or it's going to need to be moved into the thread. But with scope threads, we can do this now. And the way you do that is you create a scope, and then from within that scope, you can spawn threads. And it knows that when that scope ends, all those threads are going to be joined, and you have no problem. Therefore, you could use this outer type because you know that it's only going to be used in the context that it's alive. For async, I kind of mentioned that there's kind of parallels in terms of data handling. There's nothing out of the box like that. There's some crates like Tokio scoped, but these have significant drawbacks because when the scope exit, it blocks until every future spawned by the scope completes. So you kind of get this blocking behavior. And it's not really designed for this use. So I don't know if there's ever going to be any plans to bring in this type of behavior for async things. But it's an interesting thing to think about anyway. And I realize I've gone fairly fast, but there's a bunch of things I haven't talked about, and maybe we can talk about a bit afterwards. So I haven't talked about errors and exception handling. I haven't talked about canceling tasks, which you might do with the select macro. Or in futures, there's this future abortable. I haven't really talked about passing around data very much. I haven't talked about the different types of mutexes. You can get this interesting thing where if you've got that mutex lock type, you could have one task that's locked, that's kind of basically paused because it's waiting for this mutex to be available. It's kind of just waiting for the mutex, and then you could have another thread which is holding that mutex, but it's yielded because it's waiting for something else, like something on a port. So in those very specific cases, you might want a mutex that when it can't take the lock, yields instead. It kind of treats it like you would treat waiting on a port, where you say, I can't do any more work, just return back to the executor, and the executor can do something else instead. I haven't talked about pinning, just do with where the data is. And I haven't talked about task wake up. So there's lots of scope if anyone wants to do another talk or if you want to carry on the conversation about it on async, because it's a huge topic with a lot of interesting stuff in. But I hope this has served as like a good primer. The conclusions, I really like that quote. Threads are for working in parallel. Async is for waiting in parallel. It's a really nice way of thinking about it. Rust provides simple syntax out of the box, and then these third-party libraries like Tokio and async-std provide user-friendly runtimes, allowing you to quite quickly get writing asynchronous code. And there's constant development in this area, so we should expect kind of constant improvements, hopefully, and these things just becoming not necessarily easier to understand, but like definitely more user-friendly. I'll put a bunch of links in the chat because I found a ton of useful things. The async book, Tokio tutorial, async-std book. So if anyone wants to do a follow-on talk or just wants to read up about it, I've got quite a few links that I thought were worth sharing. So shall we open the floor for discussion?
Well, thanks very much for taking us through that, Ciara. I do have one less technical question. So you mentioned that it's constantly being worked on and improved upon. Do you know of anything coming up in the pipeline for the development of Rust, of the Rust language, where there's any new features on the horizon, or is it just something that's re-examined frequently?
I think async trait is something some people want, and then that kind of interoperability between runtimes seems to come up against a lot. Haven't got into it here because I would need to read up more on it, but stuff to do with async destructors, I think, is things that people want. So there is, little things like that. But I don't know. Maybe if anyone else on the call knows, I'd also be interested to know if there's anything to look out for.
There is definitely that interoperability being discussed, right? Because right now, because of different runtimes and they not being compatible with each other, there is a fracture or a partitioning in the Rust system, right? So they definitely work around that. I've heard on some of the podcasts with the people. I think there is a async group doing or trying to make those decisions.
Yeah, it'd be cool if they do manage to get some unity in it so that we can use things freely.
Yeah, also, but I think it's not a problem of Rust async, but basically the bug in async is usually kind of difficult, right? Because async makes kind of the things event-driven programming, right? So if something goes wrong, you get a backtrace, for instance, you don't get a backtrace of all the calls that basically got you to that situation from the main function, right? You would be just having a call backtrace from the executor code. I think Tokio is trying to somehow help in that, but I'm not sure what the progress is there. Yeah.
I feel like is like tracing related, like tracing crates. Is that something people use for like debugging these things?
I mean, so tracing probably, yes, could help, but it would produce the traces, right? So that's a separate,
exactly
separate
the same
thing. Whereas I think Tokio is trying to, or Tokio IO is trying to do something more around backtracing it, right? So somehow marking maybe the events and then being able to backtrace it to the calling events and so on. And apparently Tokio is also working on a console so that you can have something like a task manager view of your tasks inside the Tokio runtime, which is also nice, right? So you can in an easier way potentially analyze performance bottlenecks and so get some statistics from your from how the code is getting executed.
That sounds super useful. Monitoring. big programs.
Hey,
Hello.
Just one note, which I found really interesting, is that if so, the runtime is a static thing that is kind of implicitly carried over to all your async functions, and then when you await, then that being executed on the runtime. But I think you can also do it explicitly. So basically, you can introduce multiple runtimes, and you can decide where you want to run that polling of the future. And I think this might be useful if you want to prioritize some of the functions. So have a runtime that only executes high priority tasks, and then another runtime that does lower priority ones.
Yeah, definitely. I've also heard this. I haven't done it myself, but yeah, I know that you can definitely create multiple runtimes and then specifically spawn threads on a particular runtime instead of just into the wind.
We've had a couple of questions coming in the chat as well. So we've had one. Great talk, Ciara. I was going to ask about any problems returning result objects from async functions or spawn threads. I'm trying to think through error handling.
So returning result objects is kind of totally fine. You handle them exactly like you do normal types, which is one thing that's kind of really nice about asynchronous code, is it just looks like synchronous code. I haven't gone into exception handling purely because I need to read up on it and I don't want to tell anyone anything that's wrong. So if anyone else wants to chime in on exception handling, like if it panics, what the actual process is there, I'd be interested. But I guess in most Rust code, you shouldn't, touch wood, have many panics. And if there is a panic, it means you're going to shut down. You're trying to shut down anyway. So yeah, future research for me to do and to read up on.
There was another one as well. Is there no hope for runtime interoperability without async traits in core?
I'm sort of not aware of them being dependent on each other necessarily, but although actually, yeah, no, the async read and async write, yeah. I don't know if it would need to go into core. Another third party that they just kind of both become dependent on presumably would also work in terms of making the major ones compatible with each other, I would think. But I'd need to read up on what the people who are actually working on its hopes are for interoperability, because I'd just be speculating wildly.
can you hear me?
Yes.
Oh, perfect. Yeah, I have a quick question regarding the presentation that I had forever for async. So just to be clear, when we go back to the TCP example and we bind to the port, it blocks on that await, right? But from my understanding, futures don't do anything unless you await them. And basically, yeah, sorry, I'll let you go back to this slide. Then it's yeah, exactly. Actually, the one before where we didn't spawn the Tokio task. Yeah. So you said at that step we block, right? So this await blocks.
Blocks not quite the right word. Like I think
okay.
it ceases execution of this particular function. So if this was in another function somewhere, then what await does is it yields back to the executor. Right. So although this code doesn't continue, there might be other code somewhere else that can continue. So it doesn't block everything. What it does is it adds it to the set of futures that it's going to be polling. And because we've used TCP listener that's within the Tokio crate. Tokio's aware of this port, and it says, it uses MIO to interrupt the operating system and say, look, you don't need to wake me up. If this was the only thing it had to do, it would say, look, wake me up when something happens here. It's not going to block exactly.
Okay. I think then this was a misunderstanding, because the way that I understood it, futures don't do anything unless you poll them, and this await kind of initiates the first poll and then yields back to the executor and all the other stuff that's happening, the waker and so on. But at this stage, if it was basically waiting until this is done or whatever, then we didn't need to be async. But maybe this was a misunderstanding on my part. So it basically recognizes or it registers this future with the Tokio runtime in this case, and
That's my understanding of it anyway. Yeah.
Oh yeah.
I will caveat everything with that.
The other thing that I was always wondering, how to do single-threaded async if so you await on something or you poll something, right, and then the program execution does something else. But if it's only on a single thread, then where is the thing that monitors, for example, epoll and would call the wake function on the future, not on the future, but on the waker and on the task and all the stuff that's involved? So single threaded never really made sense to me, because something has to, and I think it was the last point where you said we didn't really talk how tasks are awakened and stuff. I never really understood where's the thing that's living the whole time and recognizing something changed and then says, hey, this future can be polled again, if it's only happening on a single thread. But yeah.
I mean, I guess it'll come down to however the operating system handles that anyway. So if you have a single threaded piece of hardware, it's going to have an operating system that's going to have to deal with that. It can't just so that's the bit. There's this, that will have this outer loop that's going to do a bit of this, a bit of that, a bit of something else, and it's that operating system one that then what Tokio does and what async-std does is they defer. What they're able to do is say, look, I know that I'm currently waiting on something from the operating system. So rather than constantly checking, I'm just going to ask the operating system to wake me up when something changes.
When September ends, yeah. All right, perfect. Thank you.
Just as an addition, right? Even if you have a single-threaded operating system, you can still invoke epoll or poll select, right? With a timeout. So you wait on waitable objects for a period of time, and then after you exit that epoll because nothing happened, you can check potentially your non-pollable things, right? If they have finished or not. I think that can be done that way, right?
Yeah, exactly.
It's just you wouldn't be getting it potentially in a timely manner.
Yeah.
We haven't got any more questions in the chat, Ciara, but seeing as we've got a bit of time, I was wondering if it's worth going through some of the. We've only got one more talk lined up for the next immediate future, haven't we?
Yeah. So we have Chris's talk in 2 weeks on the 28th on C++ Juice, building an audio plugin, which should be cool. And then I think the plan after that is maybe the joint meetup with we'll wait and see. I will watch this space. But yeah, we've got as well. Yeah, I think we've got a couple of people who've indicated that they might do a talk, but they haven't committed to a date yet. So yeah, if anyone here would fancy doing a talk, it's a really nice, I think, excuse to look into something and check your understanding of it. And we're a very friendly bunch, so don't be scared.
All skill sets welcome.
Definitely. And it doesn't have to be on something like async, which I know is a bit of a it's just one of those topics. But there are it can be on anything that that you think that might be interesting, as long as it's Rust and C++ related. We'll like to hear it.
It actually occurred to me something we haven't had for a while is somebody just talk about a small pet project that they've done with Rust. So not necessarily picking a particular feature of the language to go and learn, just I wanted to implement some use case and here's how I got on, and some lessons learned along the way. Even something like that would be wonderful, I think, if anyone was interested.
I'm just going to stop sharing and dump those links into the chat in case anyone wants them. There are so many more links that I could have put, but I tried to be,
And when we upload this to YouTube, we'll add the links then as well into the, what's it called? The video description.
Yeah.
And I'll just repost the Discord group as well for anyone who joined partway through. Getting a couple of thank yous. You're welcome, guys. If there's no more questions, we'll give people a minute or two to save the links, and then we'll call it there, I suppose.